You've probably heard that black holes can rip entire stars into atoms. But honestly, that's not even the most terrifying thing they do. Black holes are powerful enough to shred stars, yes, but the real shock is that they might be able to permanently erase information from the universe. If that's true, it would break physics as we know it, tearing up the rule book that has guided us for a century. So today, we're going on a cosmic journey. First, we'll explain what black holes really are. Then, we'll talk about what physicists actually mean when they say information. And finally, we'll see why the clash between these two concepts creates one of the biggest mysteries in science: the black hole information paradox. Let's start with the basics. A black hole is what you get when you pack an enormous amount of mass into an unbelievably tiny space. Imagine crushing a mountain down to the size of a grain of sand. The gravity at the center of a black hole becomes so extreme that it can tear matter apart, ripping it into its most fundamental elementary particles. Nothing, not even light, can escape its pull once it gets too close. This point of no return has a name: the event horizon. The best way to think about it is like riding a river that you don't realize is heading for a giant waterfall. There's an invisible line in the water where the current becomes too strong to fight. Once you cross that point, no amount of swimming will save you. You're going over the edge. The event horizon is that invisible line for a black hole. Cross it, and you can't come back. Because light itself can't escape from inside the event horizon, we can't directly see what's going on in there. It's a literal black box. But physics gives us some powerful clues about what happens at the edges of a black hole. And it's those clues that lead us directly into a major, universe-breaking problem. This problem starts with one of the most brilliant minds in history: Stephen Hawking. He discovered something incredible. Black holes aren't completely black. They emit a faint glow of particles, now known as Hawking radiation. This radiation carries away a tiny bit of the black hole's energy and mass. It's like an unbelievably slow leak. Over unimaginable lengths of time, this slow leak means a black hole can eventually evaporate completely, vanishing into a final puff of radiation. And when I say unimaginable timescales, I mean it. For a black hole the mass of our Sun, the time it would take to evaporate is vastly, vastly longer than the current age of the universe. We're talking about a 1 with over 60 zeros after it. These numbers are so huge they almost lose all meaning. But in the world of theoretical physics, if something is possible, it's inevitable. The theory tells us that, given enough time, every black hole will disappear. Okay, so black holes evaporate. Why is that a problem? To understand that, we need to talk about information. In physics, information isn't about secrets or data on a computer. It refers to the unique, specific arrangement of every particle in an object. It's the quantum blueprint that makes a diamond different from a lump of coal, even though both are made of carbon. It's the precise pattern that distinguishes a squirrel from a banana. Everything has a unique quantum information signature. Now, one of the most fundamental rules of quantum mechanics is that information cannot be destroyed. Ever. It can be scrambled, rearranged, or transformed, but it can never be truly erased from the universe. Think about burning a piece of paper. It looks like the information, the words written on it, is gone. But in principle, if you could collect every single particle of ash, smoke, and heat that was released, you could reconstruct the original piece of paper. The information is still out there, just in a very messy form. This is a cornerstone of modern physics. And here is where the paradox finally crashes together. A black hole swallows things with very distinct information: a star, a planet, an astronaut. All that unique information falls past the event horizon. Then, over eons, the black hole evaporates by emitting Hawking radiation. The problem is, this radiation seems to be completely random and thermal. It doesn't seem to contain any of the specific information that fell in. It's like throwing a whole library of unique books into a furnace and getting nothing but identical blank pages out of the smokestack. The black hole is gone, and the information that made up the star, the planet, and the astronaut appears to be gone with it. This directly violates the rule that information can never be lost. So what gives? Physicists are faced with a few radical possibilities, and none of them are comfortable. The first option is the most terrifying. Maybe information really is lost. Maybe black holes are the one place in the universe where the laws of quantum mechanics break down. If that's true, we'd have to throw out and rewrite one of the pillars of modern physics. It's a thrilling thought for a theorist, but it's also a deeply unsettling one. Why? Because if information can be permanently destroyed, it doesn't just break one small rule. It shatters our understanding of cause and effect. The idea that the present state of the universe contains all the information from the past would be wrong. Our ability to predict the future, even in principle, would collapse. The very foundations of reality as we describe it would crumble. We would need entirely new laws of nature, and right now, nobody has any idea what those new laws would look like. That brings us to option 2. Maybe the information isn't destroyed, it's just hidden from us. Some theories propose that when a black hole evaporates, the information escapes into a tiny, new baby universe that buds off from our own, forever disconnected. Another idea is that a microscopic, stable remnant is left behind after the black hole evaporates, holding all the information like a tiny cosmic hard drive. Mathematically, this is a comforting idea because it saves the laws of physics. But practically, it's not very helpful. If the information is locked away in a baby universe we can never access, or a remnant we can never read, it's functionally lost to us. It's like your data being saved, but on a hard drive that's been thrown into another dimension. The rules of physics are rescued on paper, but our ability to actually test or verify them vanishes completely. This leads us to the third, and perhaps most popular option today. The information is preserved, but in a completely mind-bending way. Instead of falling into the black hole and getting trapped inside, the information gets imprinted onto the black hole's surface, the event horizon itself. Here's an analogy. Imagine you have a messy room completely filled with laundry. Every time you add another piece of clothing, the room itself has to get a little bit bigger to hold it. A black hole seems to do something similar. It turns out that for every bit of information that a black hole swallows, its surface area increases by one tiny fundamental unit, a patch of space about 10 to the power of minus 66 square centimeters. This suggests that the information isn't going inside, it's being written onto the surface. This radical idea is called the holographic principle. It proposes that all the information about what's inside a three-dimensional volume of space can be fully described or encoded on its two-dimensional boundary. For a black hole, this means that everything that has ever fallen in, all those 3D stars and planets, is stored as a complex hologram on the 2D surface of the event horizon. So how does this holographic idea fix the paradox? Well, if all the information is sitting right there on the surface of the event horizon, then it's no longer trapped inside. As the black hole emits Hawking radiation, that radiation originates from the edge of the event horizon. This means it can interact with the information stored on the surface, picking it up and carrying it away as the black hole slowly shrinks and evaporates. The information isn't destroyed. It's slowly and carefully leaked back out into the universe, encoded in the outgoing radiation. The library isn't burned. It's just released one scrambled letter at a time. The laws of quantum mechanics are saved. But the implications of this are absolutely staggering. If this holographic principle is true for black holes, why not for the rest of the universe? It suggests the wild possibility that our entire three-dimensional reality might be a holographic projection of information stored on a distant, two-dimensional surface at the edge of the cosmos. Our perception of depth and the third dimension could be an emergent property, like a 3D image rising from a 2D hologram. Is it mind-bending? Absolutely. But it's a serious idea being explored by some of the world's top physicists. The information paradox forces us to confront the limits of our knowledge. Either our most fundamental laws of physics are wrong, information gets hidden away in places we can never reach, or we live in a holographic universe. Whatever the final answer is, it's clear that black holes aren't just cosmic vacuum cleaners. They are theoretical laboratories that hold the potential keys to unlocking the deepest nature of reality itself. If you want to dive deeper into these incredible ideas, make sure to subscribe. In our next video, we'll start unpacking the bizarre math and theories behind the holographic principle. Thanks for watching.